Bueno, vamos a empezar. Cierra la puerta, Mariano, empezamos aquí que la cierren.
That is
Ernesto was a member of the Scientific Advisory Committee of Dictionary for 4 years. Bueno, vamos a empezar. Buenos días. ¿Se oye? Sí. Como no hay jefes de mayor rango, yo voy a presentar a Anders Persson, un sueco que estuvo primeramente muchos años en el sistema meteorológico sueco, empezando como predictor en las épocas clásicas de los años 60, casi sin predicción numérica. Después fue contratado por el Centro Europeo, estuvo allí muchos años en el departamento de operaciones y ya desde el principio mostró un interés especial por lo que hay detrás de los modelos, ¿no? Y por diferenciar un poco entre los modelizadores y los predictores, donde, como él dice, hay una guerra que se estableció cuando los modelizadores empezaron a decir que en 5 o 10 años no se necesitarían predictores. Después estuvo también en la Met Office como consultor en el Servicio Meteorológico Inglés, y como ha estado explicando en una pequeña reunión que hemos tenido con los predictores de la sala, cuando él pensaba que al retirarse se dedicaría a la historia, que es lo que de verdad le gusta, le han empezado a solicitar dar charlas en muchos sitios sobre los temas de los que él es especialista, es la predicción práctica. Entonces de eso es lo que nos va a hablar, y no me entretengo mucho más porque luego puede haber preguntas. No, al final vamos a usar el ratón. Muchísimas gracias, perdón por molestar a José Antonio, pero es que si no lo ven desde las delegaciones, a las que, por cierto, buenos días a todas las delegaciones. Luego habrá un turno de preguntas, no muy largo, porque a la 1:30 tiene que salir para el aeropuerto Anders, que, por cierto, nos ha hecho este favor de una manera totalmente desinteresada el venir aquí y a dar esta charla. Inicialmente había venido contratado por la Asociación de Comunicadores, ayer estuvo dando una charla, pero ahora va a dar aquí sobre estos temas. Y no me extiendo más. Very many thanks for coming, Anders.
I'm very pleased and honored to be here in Spain and talk to you, and I hope I have something to say. It happened to me 2 years ago. I was living in Finland, and I was out in the forest, and I had a phone call on my mobile from Barcelona. Do you want to come to Barcelona? And of course, who doesn't want to come to Barcelona? And they wanted me to talk about what I have developed ideas from my time at the European Centre in the user guide about the forecaster as an intuitive statistician. And when I came to Barcelona, I was a bit shocked that all Spain would see and listen to me. So some of you might already have seen me develop why I think that weather forecasters, just like politicians, economists, military, other decision makers, live in a flow of information, and they must make rapid decisions. And then they have to develop, whether they are aware of it or not, something that is called intuitive statistics. And I have developed that concept more for forecasters, and I will do to add today further, I hope, insights since my talk in Barcelona. First of all, very much in probability in weather forecasting deals directly, indirectly about probabilities, in numbers or not, as I will develop. Probability forecasting as such is controversial politically, because it leaves to the decision maker to make up his mind. A deterministic forecast, rain, will more or less tell people what to do, bring an umbrella. But the 30% risk is of course up to you to decide is a risk worth taking. There's nobody to blame if you make the wrong decision. It's also scientifically controversial. deterministic models versus probabilistic, and the interpretation is not always easy. And third, there is also philosophical implications in probabilities, which I will come back to. But first, the political controversy. And this is an authentic phrase, not the man, but what you said here, I've heard from one of the member states' directors at European Centre that we want better forecast, not some blood index telling us how bad the forecast is. And of course we all want perfect forecast, but we have to wait for some time, and during those 100 or 150 years we must cope with that the forecasts are not perfect, and make the best out of this. And my message, I saw three main messages. First of all, the forecasts are not perfect, so why try to appear as if they were perfect, as I do in some countries, presenting hour by hour forecast of temperatures or rainfall with decimals, as if that were absolute accuracy. And secondly, we also know that telling about the uncertainty increases the value of the forecast for the user. He can make better decisions. And what I think I have found is that it also is good for the forecaster. It is in uncertain situation that the forecaster really can show his skill, experience, etc. So it's also a good thing for the forecaster to make use of uncertainty, turn a bad thing to a good thing. Scientifically controversial, as you have perhaps learned, probability came into science only 400-500 years ago, and it was in connection with gambling. But the strange thing is that we have been gambling for 10,000 of years. Here's from the old Greek, playing a game, and even from the Stone Age we have evidence that people were gambling. So why did it take so long until gambling became sort of scientifically explained? The reason is that people were not aware of randomness. Everything was supposed to be decided by the gods. Or when we became Christians, God himself. So there was no randomness. Even so, when we wanted to know his will, we threw a die to know if this lady was a witch or not. The die was a message from God if she should be killed or not. So there was no notion of randomness. And although today, when you are playing and somebody is winning in Monte Carlo, the gods are on his side, if you say. He has a lucky day, as if still something was decided out of our control. So the notion of randomness still has to be understood by us. And that's why probabilities have problems already as late as today. And one interesting implication in this is that as late as in the 1700s, when the measurements were normally done by astronomers, the position of Jupiter. And they make many measurements of the position of Jupiter in that evening, and then they put down in the log the best value, the value that they felt was the most accurate, not the average as we would have done, because they thought that if you make an average, all the errors add up. Instead of, as we know, they randomly cancel out. And thirdly, they were not happy with many observations, because that would cause these problems. So this is the situation in the 1760s, when at least people have started to think about randomness. And by the way, what made people start to think about randomness was the destruction of Lisbon in 1755, an earthquake and tsunami, because it was felt that whatever bad the Portuguese had done, God didn't deserve to punish them that hard. So perhaps there was some things happening outside his control. So the tsunami in Lisbon has a sort of a scientific importance to make people realize that things might happen at random. But now, when I discuss with forecasters, I sometimes feel like I'm on a time travel back to 1760s. Because when forecasters have many options, many models, many of them tend to, now which one should I follow? Which one is the best? Which one is the model of the day, instead of making a weighted average? And they feel uncomfortable to have many models. They would prefer just to have one. And also the average, weighted average, they don't like, because as with the astronomers, the mean of the observations might fall between the observations and not represent the real observation. And in the same way, the average, weighted average of forecast might give something that does not match any of the models and might even look unrealistic. So, in some sense, I feel somewhat back to the 1760s, just after the Lisbon catastrophe. And the paradox here is that we, even if we have probabilities, we still will give out deterministic single value forecast. And when I was at the Met office, there were big debates about the best data policy. Best data means the agreed forecast, the one that should be put to the customers, on the web, and it should be the same forecast for everybody. And there were debates if there is only one forecast. I had the opinion that there are different forecasts depending on who you are, but never mind. The policy was to have one forecast and the best forecast. And the paradox is that probabilities are easy to compute. For example, the proportion of members in the 50-member ensemble from ECNWF having rain, but difficult to understand, interpret, and use perhaps. Vice versa, categorical values like the best data are easy to understand, 17 meters per second, 8 degrees. But obviously it's difficult to compute, because Ken Milne, one of the leading guys at the Met Office, told me last week in Reading, they are still debating how to construct this best data. And the problem briefly is that should they use the ensemble mean or median, or take the value from the most favored model, the Met Office model, in our case the European Centre model. And there are pros and cons in this. One is that the most favored NWP model is physically realistic. The forecasts always look realistic as a snapshot from the atmosphere. Everything is consistent, almost. But of course, they are jumpy. They change from one run to the other, which in my experience and the Met Office experience is as annoying to the public as a forecast being wrong. A bad 5-day forecast takes 5 days to discover. A jumpy 5-day forecast takes 12 hours to discover. So the jumpiness is a very important issue, and the single model production gives a lot of jumpiness that is annoying. On the other hand, some sort of averaging, minimizing the errors, more accurate, much more stable, but of course there might be problems with the physical consistency. But these things, I think, must be, as at the Met Office, debated, the pros and cons, and not just take the easy way, as my country and Norway has done, to put out the last ECNWF forecast on the web with decimals. That, I think, is not honest. The philosophical controversy with probabilities is that we don't really know what probabilities are. There are different definitions. There's one classical, that is tossing a coin or tossing a die, the chance of having a 6 twice, etc. That's a classical probability. The frequentist probability is the one that normally is taught or has been taught. That is, for example, the probability of rain in Madrid over a year is the number of rain days divided by 365. That is a frequentist definition of probability of rain. That is a traditional school in statistics. And against that has been lurking in the background with increasing insistence to be recognized, a subjective approach, sometimes called Bayesian approach, which is subjective. So it means I go out and I see the clouds thickening, and I tell somebody, well, I think there will be rain today, perhaps 40% chance of rain. That is based very loosely on my experience of clouds and Lisbon, and Madrid, etc. So that is not as stringent as a frequentist. But there are, as always, pros and cons. And the limitation of the frequentist definition we all know about from the Concorde disaster, where before the crash, Concorde was the absolute safest plane in the world, with 0 accidents over 100,000 hours. And just in a few seconds became the most unsafe airplane in the world, because 1 over 100,000 is much more than for any other aircraft. So it shows the unrealism in basing the probabilities just on a frequentist approach. And from similar studies we know that not in Concorde case, but in other similar disasters, like the Harrisburg disaster in America in 1977, the nuclear power station that broke down, there had been subjective Bayesian estimate that something could happen. The chance was not 0. And in the same way, the chance obviously was not 0 for Concorde even before the crash. But that had to be based on more subjective Bayesian approaches. Another way to illustrate this is the football match between, let's say, Sweden and Denmark. And 12 minutes left, Sweden is in the lead with 1-0. Then a frequentist, die-hard frequentist, might sit there and watch the game, and in comes a Norwegian offering him a bet, 1 to 100, that Denmark will win. And then, of course, he must make a decision, should he take the bet or not. And it can only be done on a subjective basis about how the game had developed. Was it a lucky goal, a Danish own goal, or are the Danes more skillful after all and had just bad luck? He must make some sort of subjective opinion to see if he should accept the Norwegian bet or not. There is no escape. So in this case, he has some probability density function that the odds for Sweden scoring more in the end is slightly higher than Denmark scoring in the end. But then suddenly something happens, Sweden scores another goal. Then, of course, the whole probability of Denmark winning will decrease, but still there is a small chance after all, and we have seen that happen in the history of football, that the other team will in the end make these 3 goals, but it's a very small chance. So it's sort of a reflection of that subjective probabilities, even if they are not stringently defined, must be dealt with, because that is part of our life. And there are now many good books about intuitive statistics, uncertainty, and also this subjective approach. And the one that I highly recommend is this one. Have any of you seen it or read it? It's Daniel Kahneman. He was a Nobel Prize winner in economy in 2002, and he got that because he investigated how people really think in business, not how they should think. And it's a very good read, because at least when I read it, I found, this is how we meteorologists also tend to make our mistakes. So I more or less translating this book into meteorology just now as much as I can. Then about Bayesianism, there's a book, I think not in Spanish, but it's a very good read, because it means that the problem with Bayesian statistics is not the mathematics, but the philosophy about is a subjective probability or not. So I would like to initiate a course, a 1-week course in probabilities that would first start with the 3 different definitions of probability. So the first day about the classical definition of probability, the second day frequentist definition, third day the subjective probability definition. On Thursday, decision making from probabilities. And finally, the psychology, how to misunderstand probabilities, which is sort of very important to know. So just a brief outline. And on the user meeting last week, I had a poster at the ECNWF. So if you go into the ECNWF home web page on the meetings, the user meetings, you will see the poster where I have the same, slightly more elaborate details. So the classical definition will, for example, solve a problem that I know some people have been struggling with, how to add probabilities. So if you have the 20% chance of rain or whatever in the morning, and in the afternoon it's 30%, what is then the risk for rain the whole day, or in both intervals, or any time during the day? That is not possible to solve just with this information. You must also know, so here is the rain during the whole day, and in both, sometime during the day, and in both periods of the day. So you must also know this value to be able to make this addition, and not everybody is aware of this. And in this case, it means that it will rain sometime during the day is 43%, and that it will rain both periods, in the morning and in the afternoon, is just 7%. But this is not trivial from just the first values. And then something I want to repeat from Barcelona, because it has forecast implication, is the regression to the mean. It is a very important artifact. It can both mislead us and it can help us. So here is a meteorogram from Barcelona, from my visit there in 2012, and you are familiar with these epsograms, I think, from, is that? You have seen them, so I don't need to explain the details. So what you see here is a warm period, and then it gets cooler. And the important thing is that this cooling is not a dynamical cooling in the sense that cold air is coming from somewhere and cooling down. It's a statistical effect that there is no skill, that the system spreads out around the whole climatological frequency. And since the first period is warmer than normal, it means that it is cooling just to become normal. So it's a statistical effect and not a dynamical effect. It's called regression to the mean. And one of my favorite EPS grams is not the upper one, but the lower one, which you can find with some effort on the ECNWF website, where the modeled climate is in the background. And then, so it's the same forecast, but now you can see more clearly that there is no skill, no predictive skill in this forecast, because the median for the last 3 or 4 or 5 days is more or less same as a modeled climate. And the spread is about the same as a climatological spread. So there is the information the last 4 days is just the climatological information. And that can help you to tell in a 15-day forecast what is the predictive signal and what is climate. Climate is still useful to tell people, so it's not useless, but it's not the predictive signal. So here is a very schematic. There is some weather of some kind and a 12-day forecast. And to be able to relate this, you must look at the model climate in the background. And then you have the median, and you have the spread around the median. So this is what you see on the ECNWF EPS grams. Now the first 3-day forecast, it is lower, the value, the median is lower than normal. If its temperature is colder than normal. And there is also quite small spread. So here is a clear predictive signal. It definitely will be colder than normal on day 3. On day 6, the median is the same as the climate. But that does not exclude that it's still a predictive signal. It's just that it is sort of unlucky to have the same value as the climate. But the small spread indicates that this forecast is certain. So here is another predictive signal on day 6. On day 9, there's very large spread. So in that sense, the forecast is very uncertain. On the other hand, the median is well below the climatological average. So even with this large spread, there is important information to gain from this 9-day forecast. Only the last forecast, the 12-day forecast, the median is the same as the climatological average. And the spread is the same as the climatological spread. So this forecast does not add anything to a general tourist brochure information about the climate and the weather. So it means that the combination of these boxes and the underlying climate can tell you for every forecast where the predictive signal ends. And you will sometimes find that it ends already perhaps on day 4 or 5 in difficult situation, and then comes back on day 6 or 7. So it relates the skill of the forecast in a very useful way. But it takes a sort of an expert, like a meteorologist, to do that. So it's an argument for well-educated meteorologists as forecasters. So here the warming is mainly an atmospheric process, warm air coming from somewhere. But here is a statistical effect, the lack of skill, because it's after all a 12-day forecast. The lack of skill means that the ensemble more or less scatters along the climatological average. Then on Tuesday, the frequentist will possibly deal a lot with verification matters and statistical interpretation, because there we use historical records of observations and forecasts and make different analyses. And the one I like here is the Breyer score, because the Breyer score has a magic property. It can read your inner thoughts. And I promised on Saturday to explain that today, because there was no time on Saturday. So it's very simple. It's the PI is a probability, OI is the weather, it's either 0, it didn't happen, or it's 1, it happened. And then you square it, so it's positive, and then you add over n days. So it's very simple mathematics. But still, here is now the Breyer score as a y-axis, and the probabilities on the x-axis. And the green and yellow lines are the points, or the Breyer score points, if it rains or doesn't rain, depending on your forecast. So if you have said 100% rain and it rains, you will have 0, means very good. The lower the better for the Breyer score. But if it's dry, you will be punished with 1, the worst. And vice versa, if you say it will stay dry, and it stays dry, 0, but if it rains, 1. So it tells you, depending on your choice of probability and what happens, how you will be punished. Now, assume now that you believe and you are a good forecaster, so you have a good tuning, that the risk is 70% for rain. But then due to political circumstances, pressure, tactical considerations or whatever, you said, no, I will issue a 60%. Now, so if now you stay with this, if you are right, you will only be punished by 9 units. That is the punishment, because you have not said 100%, then you have 0. But you have 70%, so you will be punished by 9 points. Whereas if you are wrong, it will stay dry. You will be punished by 49 points. But you think that if you now say 60, now if it stays dry, you will only be punished by 36 points. And if it rains, you will be punished by 16 points. And the decrease is 13 units, and the increase is 7 units. So perhaps you should, for tactical reasons, say 60, because then you would gain some points. But then comes the whole clue. Yes, you can do that, but remember that your true belief is that it's 70% chance of rain. So this must be weighted. And if you weight 7 points by 70, then you have, well, that's a 0. So you will have, so if you weight this, you will actually achieve the opposite. Just because rain, as you believe, is much more certain, you will actually be punished more than if you stay with your true belief. So that is the background why this Brier score seems to read your inner thoughts. Now, on Wednesday, we come to the subjective probabilities. And then it's very much like the Danish-Swedish football match. You have considered all the available information, the Hirelam, Aladdin, ensemble forecast, the Spanish ensemble, observation, and you have formed some mental picture of what will happen. And then comes what happens in forecasting. In the old days, when I was a forecaster, it was observations from a lighthouse upstream, telling about rapid falling pressure or increasing wind. That sort of made us question, should we change the forecast? And it was just 5 minutes to the broadcast, so you have to make a snap decision if you should do something. Today, it might also be observations in the short range. In the medium range, it might be also that the ESA NWF forecast suddenly appears and has some message. Then the problem, and it's only 5 minutes before the broadcast or the briefing, you should, in a snap decision, should I now modify my careful, considered opinion, or should I adjust it? Very much as in the football match. And this is not easy, and there is no recipe that you can absolutely follow. It depends on a lot of things. As with the football match, why was Sweden in the lead? How are they playing? In this case, how is the weather situation? So and all this must be done in 5 minutes' time. Then perhaps when you had your briefing, then there's another briefing half an hour later. Then you have more time to think, and perhaps you come up with another modification. But this is how operational forecasting is done. You don't have unlimited time and resources and can decide when you want to give your forecast. You have to give it more or less when you perhaps don't really want to, but are forced to. And then it's a matter of making these snap decisions as good as possible. And that is, as we can see from these science books about intuitive statistics, not easily done. And we share the same problem as politicians, economists, military, who have to make snap decisions in a flow of information. So that has been, in my view, the role of the forecaster for 150 years, since Fitzroy started forecasting in Britain in 1860, whatever. But we have not been aware of the statistical element in our operational forecasting. Thursday, decision-making from probabilities. And I have been teaching the cost-loss model for 30 years at the European Centre. And it means, and I think most of you have heard about the cost-loss model, and it's still taught. And it's a good start, but it is by no means the end model. And Kahneman's book deals with a lot of later research that shows that, for example, compared to the cost-loss model, humans tend to be more eager to avoid losses than to make gains, whereas the cost-loss model assumes that gains and losses have equally pain or pleasure to humans. And that can be easily illustrated by this example. to have 80% chance of winning 1,000 euros or being given 700 euros directly in your hand. According to the cost-loss model, the first one is to be preferred because the expected gain is 800 euros. But anybody, even a professor in mathematical statistics, unless he is a millionaire, would take the second. So it means that we have to start with the cost loss, but remember it's just the start, and the decisions are made on a more complex level. And it will also help us to understand perhaps why some customers don't like good forecast, which we think are good forecast, and might prefer what we think are bad forecast. So it also will lead us to a better understanding of the reaction of the customers. They might not always be wrong. And then Friday, the psychology of probabilities, and I will come back to that in my second part. But so, for example, if 20% might not be very strong probability, but one way to sell it, one way to make people think twice, is to take, well, it's 10 times higher than normal. So that is to use psychology. In this case, it's called the base rate mechanism. I will come back to that. So it's one way to make people think twice before they say, well, 20% is nothing to bother about. Because when what sort of annoys me sometimes are two things. One is that probability forecasting is seen as something that started in 1992 with the European Centre starting ensemble forecasting. That is not true. Probability forecasting started, as I said, 100 years ago. And the paradigm shift was actually in 1980 when the European Centre came with this supernatural, exact, detailed forecast, which indicated that we don't need probabilities. And in 1985, the optimism was very high. In 1985, the 10-year plan from ECNRBF promised 12-day forecast, still up to 12 days, in 1995. So there was very high optimism about accurate deterministic forecast. And the second thing that sort of annoys me is that we talk about probabilities as if that was the only way to convey the message. And in my view, the main thing is not probabilities or not. The main thing is to convey that our forecast is not certain. And you must take that into account when you make your decision. Since all forecasts lead up to a decision. It's not just a game. They serve to lead to a decision. And knowing about the uncertainty will help you to make a better decision. And if that is done by probabilities, fine. But there are many other ways to convey this message, perhaps based on probabilities, but presented in other ways. So that's why difficulties with probabilities should not prevent us from discussing in terms of uncertainty. So there are 7 different ways, more or less starting from no uncertainty at all down to 100% probability. And the first one goes back to summer 1975. I was on holiday in England and I passed the Met Office, and in those days you could easily get a guided tour, the Met Office, and at the end I asked why it came that I always remembered the British popular Radio 4 forecast, but never the Swedish P3 forecast. And then he said, well, I don't know what you do in Sweden, but here we have a rule that for this pop music channel, we don't spend more than 30-35 words on the forecast for the UK. And that has the advantage, I like that, the advantage of filtering away less predictable and less important details. made it easier to understand and remember. It made the forecast more consistent compared to previous and more trustworthy, because less details, there is less to change. And then also they verify better because the less predictable details have been taken away. Of course, if the less predictable details were floodings or heavy rain, thunderstorms, of course they would feature in the text. But there were a lot of other things that could easily be removed, not to obscure the main message. I tried that in 1975 in Sweden, but was heavily punished and had to go back to writing these long essays which nobody understood, but everybody was impressed how detailed we could be in our forecast. But this is another example. It's from, at SMHI we have two forecast services, one meteorological and one hydrological. And in the case of flooding in 2004, there was an interesting difference how the meteorologist and the hydrologist dealt with uncertainty. So here is, after 4 days, 160 millimeter had fallen, and that is much in southern Sweden. And I think also the ground was saturated, so there were real problems. Now, on the first day, the meteorologist issued a forecast that turned out to be almost perfect. It was from the European Center, and it was more or less perfect, as we know now. Next day, they followed the European Center again, but now the maximum was supposed to come northwest. And 2 days before, the next day, they warned about severe rain in the southeast. And only the day before, they were back, but they started 4 days earlier with a good forecast. And my catch question is always, how many of these forecasts were good? And some people say, well, half were good and half were wrong. No, all were wrong, because nobody trusted any of these forecasts. The first forecast, you don't, at least in 2004, trusted a forecast 4 days ahead about heavy flooding, because they were uncertain. But then all this jumpiness meant that not even the last forecast was trusted, because the forecaster had lost the confidence of the listeners. The hydrologist, of course, in this case, they could have worked with probabilities, but they did something else. The hydrologist didn't try to impress people by details and confidence. They took the following line. 4 days ahead, that somewhere in southern Sweden, there will be 30 millimeter. So they kept everybody, at least their water authorities, on the toes. Somewhere, prepare yourself that somewhere in southern Sweden that there will be 30 millimeter. Next day they more or less repeated the forecast but excluded the extreme south. Next day they narrowed in, zoomed in on central southern Sweden. And then the day before they more or less had the same forecast as the meteorologist, with the difference that now their customers trusted the forecast. They had followed how it's that they zoomed in consistently to this target, and that's why this forecast had effect on the decision makers, but the meteorological one was not trusted at all. And here what they did was to concentrate on the predictable part and exclude the uncertainties. Which in this case, apart from details, was the position of the maximum rain. And they had the same background information as the meteorologist. So this is one way not to promise more than you can honor. It's a good moral thing also outside meteorology. Then second is this sort of verbal communication, where we have this standard phrase like likely, probable, possible, local, indicating that it will not happen everywhere and not with absolute certainty. And those can be elaborated on. I wouldn't be surprised, and it cannot be excluded, and I cannot guarantee, which sort of serves the same purpose to show that we are not absolutely certain. And then base rate, I will come back to base rate, but it's 10 times more likely. Base rate is the climatology, and it's 10 times more likely than normal. It's also a way to tell people about uncertainty in a way that they might react to. And then protective is that if I were you, and the deterministic forecast say it will rain, so I have already made a decision for you. But I think that is wrong. Probability forecast does not do that, but we can help the customer if I were you. If you know him or her and his business, you can. If I were you, I would not put out my Spanish wine on the in the garden because there might be frost, etc. And framing, and is it more or less what the hydrologists did? They sort of changed the interval, or you can by increasing the area or increasing the time interval, change a low probability to high probability. I will come back to that in a later example. Then body language. If you are on TV, there was a forecaster in England, Francis Wilson, who always scrubbed his nose when he was uncertain, or with his body language. And here, say, a person in Finland looks worried because southernmost Finland, people there might be affected by thunderstorms. And what she has conveyed is perhaps some 80% risk of thunderstorms in her worried outlook and look and the phrasing. And then if you are not visible, you are in radio, or you are briefing, or you are writing, then you can still use this trick by telling a story. So you give the background. So if you have a case of risk of frost, you can either say that there is cold air from Greenland coming down in 5 days' time, but a developing low over Britain might push it away. So you have told people about some 20% probability of cold weather without mentioning the numbers. You have also told a story like a detective novel with a police commissar and a murderer, and they are fighting and who will win. But you have given, or you can say that we have low clouds and they will disperse, but close to lakes or rivers they may stay and keep the temperature high. So by giving people the background, they will appreciate your skill more and also implicitly get a feeling for the uncertainty. You should absolutely not, which I hate, say, well, the easy model and the US model, they have cold weather, but the UK model keeps warm. But because what you do then, you take these maps and put them on your table and invite the customer to come and look and share your problems. And more or less ask him to make his own choice, what he wants. So that is, and also to blame the computer is absolutely out of my culture. And I remember I mentioned in my Barcelona talk, I had many transparencies about the case in December 2011, where the British forecaster had no clue at all what would happen because the models were very jumpy. So anything from flooding, snow or storm was possible. But instead of blaming the computer, which is jumpy, they took sort of a personal responsibility. The cyclone has changed track, and we have revised our calculations. We are in charge. We have trouble, and everybody has trouble sooner or later in his profession, so people can understand that. It's an absolute lie that the cyclone has changed track. The cyclone has its track, full stop. But she conveys a meaning that we are monitoring something, follow us, listen to our next broadcast, have confidence in us, we will keep you posted. So even if it's not very scientific, it serves the purpose of keeping the trust with the public and not promising more than they can stand for. So in this case, they only in the last days show these isobaric patterns, which they normally show, because this output from the Met Office model. And what she refers to, we have revised our calculations. It's not that they start to take out paper and pen and start to do mathematical calculations. They are waiting for the next run from the computer. But they didn't want to display the jumpiness, which was their problem. They kept it for themselves. The important thing was to keep the confidence of the British people, and they succeeded very well with that. At the end, they also put out maps showing alternative tracks. Depending on exactly where the low would come, the weather would be different. There are different opinions. Some people like that, to have two scenarios. Other people don't like it because it might be confusing. And I have no personal opinion about that. I think it's one possibility, but if people feel that it is confusing, it should not be used. Perhaps it's better to have one scenario and indicate in the scenario that we are not absolutely certain exactly where the law will pass. But that is sort of a matter of debate. They were, although from a conventional point of view, the forecast was absolutely crap. They didn't know what would happen. They managed to deal with this in a very clever way, so there were praise from the government to the BBC and the Met Office, and for the management of the BBC and the Met Office to their forecasters. And I know from my personal friends, non-meteorological friends in England, they were highly impressed. So it's a good example where the forecasters in a very difficult situation turned a disadvantage, not knowing what would happen at all, to an advantage, showing their skill and how they deserve the trust from the British public. Then impact matrices is another way, and that is the Met Office warning system. And I think it has been discussed in the Spanish Met Service, but it is a matrix where the y-axis is a probability, low probability and high. So it defines how likely the event is. The x-axis is the impact, because a low probability must still be associated with something with high impact. So it deserves some warning. So the yellow there is that to be aware of that something terrible might happen. But of course, if the probability is higher and the the consequences are severe, the color changes to orange or to red. And I must, in this matrix, the only thing that can be verified is the x-axis, the probability of the event. The impact cannot a priori be verified, because if you warn about something, people take action. So, for example, when there is a high impact of strong winds, not only that this mark comes in the red or the orange field, also on the BBC, the forecaster appears with a background of, for example, a fallen lorry. You know, lorry in Spain. Big truck. And when I worked at the Met Office, I worked in the post-processing and impact section. Some of my colleagues were involved in computing values of the impact of strong winds on lorries. So they had a forecast, more or less, of how many lorries will turn around because of the strong wind. And that decided the impact warning. But, of course, it's impossible to verify, because if now all lorry drivers are aware of this, that they will be cautious, and very few lorries will turn around. So the only way to verify is to keep this secret. Then we can say, the forecast was successful. We predicted 5 lorries to turn over and 7 turned over. Or if you publish, the forecast was a disaster, only 1 lorry turned over. So we made a bad forecast. So of course, even if the forecast cannot be verified in a normal way, they are there to serve a purpose. So that's why I think that this impact, both as a value and also a way, for example, on TV, to get a message over, not just by having warnings in colors, but for example, a picture of a turnover lorry, or very strong waves on the English Channel, or fallen trees, as photos in the background of the forecaster on TV, is to bring out the message that something is dangerously. Then we have the quasi-probabilities like intervals or plus minus, which sort of implicitly assume sort of 70-80% probability that the value will be in this interval. So you have conveyed some probability without actually mentioning the percentage. But it, of course, depending on that people understand that this is the most likely interval. You can have 100% if you have an unreasonably long interval, but that is useless. And then the base rate. I was in London, and I've been preaching about base rates. And then I committed a sin. I was on a bus. It was rainy. I was on a bus, and there were two nice ladies speaking Portuguese. And when our eyes met, I said to them, you are speaking Portuguese. They were very happy, as they assume an English man would recognize their language. And then I made my mistake. I said, the weather in Portugal must be much better. What was my error? I assumed they were Portuguese. But there are 15, 20 times more Brazilians in the world than Portuguese. So even if Portugal is a member of the EU and close to London, still, if you hear somebody speaking Portuguese in London, he's more likely to be from Brazil than from Portugal. And that is sort of application of the base rate. So, in meteorology, the base rate is climatology, and one good application of this is the extreme forecast index, which relates the probability in a specific situation to the climatological probability in a bit complex way, which I have no time to explain here, but that my user to guide makes an attempt. So here you can see where there is sort of extreme heat is likely, more likely than normal in a specific situation. So it's an application of the base rate thinking. And then when we have probabilities, is it just a matter of sort of throwing out probabilities and make people do the best? And no, because when you give out a probability, you can supplement by one of these other 6 tricks I have mentioned to sex up or explain the probability 10 times larger than normal, for example. And there's a case from Britain. There was a summer 15-20% probabilities of severe thunderstorms involving tornadoes. And Birmingham City Council got a probability forecast of that magnitude and did nothing. But another agency close by was told that somewhere in Midlands there would be somewhere in Midlands there was a 60% chance of severe thunderstorms and tornadoes. And this is the framing effect. You change the geographical area, you increase it. And that automatically increases the probability, so you have not committed any mathematical sins. You are still consistent. Or you can also increase the time interval from 3 hours to 6 hours. That will also increase. So, and of course, it's a balance, because we have had to make a balance between this. So you get a message that it's not completely unrealistic, but on the other hand, people can react upon. And from this case, people who got this forecast did something. Well, those who got the first one said, well, it's not very likely. And the base rate, 50% in some cultures mean I don't know, 50-50. And I know that, for example, in my country, that they don't issue 50%, that they rather issue 40 or 60, but not 50, because that will be misunderstood. So we have to remember that 50% means different things. It means actually I don't know when tossing a coin, but 50% for snowfall in Alicante is a very severe forecast, or 50% for sunshine only in Alicante is a bit pessimistic. So these two forecasts are actually conveying a message. That is because the base rate is 50 for the first case, so there is actually no information. But for the other two, I'm not quite sure about this 2% to 80, but it indicates that here 50% has a meaning, because the base rate is quite different. So my summary is that as long as we don't have perfect forecast, there's no point of hiding it. People know that. And to pretend that we are suddenly have become very accurate. And secondly, how we convey we know that providing uncertainty information increases the value of the forecast. And in my view, exactly how we do that is not very important. The important thing is how the receiver understands it. If he understands probability, fine. If he does not, try some other way. So probability is just one of several ways to do it. And also the good message is that it's in uncertain situation that we can display our skill, knowledge, experience. So actually we should not follow this old macho culture to pretend that we are very certain that our knees are trembling. We should not have trembling knees, but put the customer into the picture and he will understand how difficult our job is. So this is not the end of the story, but not even the end of the beginning of the story. Thank you.
Maybe any questions to Anders, firstly from the delegations. Is anybody interested maybe from...
Speak Spanish, but...
Sí. No, but they will have to put the question to you in English.
Or
anyway.
Spanish, and you can translate.
Okay. Questions in Spanish or English? Or German? Or... no veo, por lo menos lo que se ve aquí, alguna delegación. Entonces, de la sala.
Yo sí.
Uh-huh.
Por micrófonos.
Sí.
Para que lo oigan las delegaciones.
Sí. Yo lo voy pasando.
I take the micro, just allow them to hear.
Hola, hola. It was a nice talk. Thank you very much. My point is the base rate, which is indeed something really important. You talked about base rate implicitly in these lovely EPS grams with the climatology on the background, which is the same conception. It is important how to select the climatology. I mean, it's not the same if you take 30 years, 40 years, or 10 years, even in a world which is supposed to be globally warm. So, could you just say a few words about this selection of climatology?
Perhaps I didn't make it clear that the climate you saw is not the real climate. It's a model climate. And the model climate with the EC system is very good. And perhaps most of the time similar to, very close to the real climate. So there is no problem. It might be for many regions still not the real climate because of the height. The grid point might be higher than the nearest station. But the point is that the same problem of the climate be not exactly the right climate, is also affecting the forecast, which will be warmer, cooler, wetter, drier in the same degree. And the idea here is that if the forecast, as in this case, deviates from the model climate in this way, a sort of perfect forecast without these problems would deviate from the real climate in the same way. So by comparing the forecast with the model climate, we have to some degree diffused or eliminated the problem with the climate. We are comparing with the model climate, not the real climate. Is that the answer to my...
Yes.
I think this was clear enough. But take, for instance, the seasonal forecasting, Paco Doblas shows every year, here and there. They show the upper tercile of, let's say, to exceed some threshold, temperature or whatever. Even there, they use the climate model, I think. And it is not the same if you take a 30 years comparison or a 10 years comparison. I mean, it depends on the climate you pick up. I don't know if I understand this up to that extent, but I think it's important.
I perhaps would have made that clear from the start. I feel my responsibility ends at 32 days. So climate and seasonal forecast and climate, I'm happily staying away from. Secondly, when it comes to biases or mean errors, I hear sometimes talk about severe problems of that type, but I suspect that, and I have evidence to back that up, it is based on the regression to the mean effect. So, for example, I had from a member state, when I was at the European Centre, a graph of the mean error for February 2011, showing that the 15-day forecast from the European Centre for this country had no problems the first days. But then gradually the mean error increased, or rather decreased, to about 2 degrees to cold on day 15. So there was a severe a drift of the mean error from 0 to 2 degrees for a country in Europe is a severe model drift, and people were concerned. But I was lucky to tell them, I don't know if they were lucky because the European Centre people like problems to solve. So they were perhaps not lucky when I told there is no problem. Because in this February 2011, it was a warm month in this country, 2 degrees warmer than normal. And the European Centre model had no problem with that in the short range, when all the fronts and all the air masses were in the right place. But with increasing lack of skill, increasing non-systematic errors, it meant that on day 15, the forecast, which more or less had no skill, more than a climatological skill, scattered all over the climatological average and around the climatological average, as they should, because there was no skill. But of course the climatological average was in this month that was 2 degrees warmer than normal, 2 degrees colder than normal. So what appeared as a severe model drift was nothing of the kind. It was just a reflection that we don't make perfect 15-day forecast, which we are working on. So some of these ideas about problems might turn out to be non-problems. That's why we have to learn this intuitive statistics. One of the main theme in Kahneman's book is about how regression to the mean effect can fool people, not only meteorologists but also normal people. And there are more of this kind, and I try to list some of these in the user guide in the appendix.
I wanted to ask you about framing, because we are developing models high resolution models, also high resolution EES. Also, our outputs from the models are in periods more frequently than before. So really, the problem is probably to explain to the users or to the forecasters that we have signal on these high resolution models. We need to upscale the probabilities in some way in the space of time, because sometimes we have probabilities in small places on the maps. So it's difficult for us to think that we are developing high resolution models and we need to upscale to give the information, because in this way we think that we are losing some information in the upscale. It's true, or is it the way that we need to communicate the uncertainty or the probabilistic forecast problems?
But you have sort of two questions. One is about losing information because you have to upscale, and why do you have to upscale?
Because if you have high resolution models, probably you have probability of some phenomena in one place, and it's very small, and it's difficult to localize in some place in the area, or also in the time, because you have more frequently outputs from the model, and also you have many small spots.
Well, that is in my view, one of the most important questions in today's metrology about high-resolution deterministic model and slightly coarser probabilistic models. And my ideal is that, and I think Meteor France has tried that, and somebody else, to have all models, deterministic and probabilistic, in the same resolution, because that avoids the psychological problem that the probabilistic forecast comes from a worse model, and if it's worse, it's just worse by that much, and any lack in quality is compensated by the probabilistic approach. So I would prefer that all models were in the same resolution. Secondly, another thing that annoys me is that just because, I'm in favor of as high resolution as possible, as many levels as possible, and shorter time step as possible, but because we need that to make a realistic model. But the forecast, even the deterministic forecast, do not have to be presented in that. Well, it can be presented as a movie, where it looks like a radar sequence, as a movie, but that is fine. But when you have tables for specific location, they call it postcode forecast in England, then these details are not predictable. So you get jumpiness and you get differences that is reflecting the numerical noise. So that's why this high resolution forecast, which I love, should be filtered in one way or the other. And at the Met Office, they found some years ago, to their shock, that on day 2-3, the rainfall forecast from the coarse global model, the very coarse model, had the same skill as a rainfall forecast from the 1.5 kilometer model. They tried. And the reason was that all these details provided so much noise. But when they filtered this 1.5 kilometer rain forecast, so they got scales of the order of 50-70 kilometers, which after all is quite detailed. Then the skill of the 1.5 came up. But of course that would, for some of the models, would like throwing away the baby. The baby is these high resolution wonderful things. But after all, it might be nice on a Steven Spielberg movie. But as a forecast instrument, it cannot be used in that way. It must be filtered, the noise must be filtered away to bring out the signal. And that also answers the question about the EPS, because the EPS will, for this averaging, do exactly that. remove the noise, keep the signal, but then give an impression of a coarser, more robust, less detailed forecast. But we must sort of overcome this. It is also covered by Kahneman, that we are more impressed by a detailed, colorful image than a rough black and white.
Tiempo para una o dos preguntas, como mucho.
I think that must be the last one now.
Tiempo como mucho para una o dos preguntas, o bien de las delegaciones, porque si no perderán avión alguno. Bueno, así veo ya al final.
Hi, Anders. Just a question for forecasters, okay?
Yes?
Sometimes we face that we have, for example, 50 members of a similar prediction system, and there are only 2 members that you have very bad weather, okay? Mm-hmm. And the others members you have, for example, a sunny day, okay? We usually, as forecasters, we filter out that information, okay? We are going to be aware in case that the real atmosphere goes in that way, okay? But we filter out that information. But there is a risk in that 2 members. According, you have to explain to us what you can do to communicate this information to the customers. We have some opportunity to do that. Thank you.
Well, 2 members having something is just 4%. And for most applications, you are right to not convey that message. But I can't exclude situations where, for example, if you intend to have a party for the new king, or something that the fact that this you can't exclude rain might be important. But that depends on the situation. So, and then of course, if it's 4% for something terrible, like a flooding like in 1982, then perhaps you should tell people that we can't exclude. So it depends very much, like the impact matrix. What is at stake? What is the circumstances? And that, I think, is the strong side with ensemble forecasting, probability forecasting, and that sort of motivates why we still have forecasters, although they have been prophetized to be have gone long time ago. That we need people who, in this information flow, make sense of it and conveys the information to the users, and perhaps different information depending on the user. And to make it more perhaps realistic, if it's 30% chance of 2 millimeter, at least in my country, the farmers wouldn't bother very much about that. They would treat it as dry. But an artist having an outdoor exhibition does not want to ruin his aquarelles by a shower or rain. So depending on who you are, you will take different actions. And the customers, the public, is not always able to do that. So that's why the forecasters and meteorologists have to learn this intuitive statistics. So when they have a chance, both on TV, radio, or in personal contacts, advise people what they should do. So that I still see that as a, and from this meeting on Saturday, which were about communicating, and all these people there were communicators. I was very happy because it was not only a matter of being pretty and smooth talking. It was quite advanced discussions that we had. So to be a communicator is actually, I would say, demands a lot of knowledge about meteorology, about models, about probability. So it's not just a pretty face. And that's why I think more than professional communicators should look into this and also become more aware of, if I know experience, I have intuition, what does that really mean? And how can I improve on that apart from just staying on in my job? How can I better assimilate and also become aware of what in my experience is actually not true, it's urban legends, and what is true and what can be improved on. So that's why I see a reason why we still have forecasters, and also why we will have forecasters 100 years on.
¿Alguien más? Si no, para ir seguros, si Anders, en nombre de todos, y otra vez más después de 2 años que estuviste en Barcelona y ahora aquí, muchas gracias y sigue ayudándonos a poner los pies en el suelo. Muchas gracias.